about anybody?
3 plus 3 plus 3.
Yeah.
So we're going to get that.
8.
8. Roughly. Okay. So basically, this is just to get you comfortable with this whole idea of multiplying one domain is equivalent to adding in the other domain. One other thing to notice, or one other thing that you'll often see.
Sorry, wouldn't that be 6?
No.
3 plus 3 plus 3?
3 plus 3 plus 3. 2 times 2 times 2.
Oh, multiply, sorry.
Yeah. Okay. If you see dBm, does anybody know what that means? It's decibels reference to 1 milliwatt. So what that means is if I tell you a signal's power is 20 dBm, okay, 20 dB is what? In real terms? 100. So that's equal to 100 milliwatts. You may also see dBW. Yeah. dBW is dB reference to a watt. So in that case, 20 dBW is 100 watts. Okay, so there's your reminder on decibels. So link budgets are expressed as power, not amplitude. And in dB. So basically it's the way I told you in the beginning. So your budget, you start with your assets and you subtract your liabilities, and hopefully at the end you will get the number you want. So in the link budget, what you do is you take the starting power, starting transmitter power, and then you add all the gains, and you subtract all the losses. So if you look at a real link budget, they will contain an awful lot of factors, each representing specific gains and losses that the system designers are interested in. So this is a fairly basic example, but it encapsulates the idea. So if you record 1, so your received power, PR, will be equal to transmit power, PT. Okay, we add the gains. So there's a gain at the transmitter, which refers to the shape of the antenna pattern. So in other words, the GT. So this is let me write down what these are as I go. This is received power. This is transmit power. This is the shaping gain of the transmit antenna. So this is 0 if the transmit antenna is what's called isotropic. In other words, it's radiating in all directions the same way. And it's positive if the transmit antenna is focusing its energy on you. Similarly, there's such a gain at the receiver. GR is the receiver antenna. And now we start with, those are the only significant gains in this model. We'll subtract LP, which is path loss. We'll subtract LF, which we're going to call our multipath fading margin. And then we're going to subtract what I call the cop-out term, LO, which is other losses. So if you start out with, let's say, 30 dBm, in other words, how much power would that be, 30 dBm? 1,000 milliwatts, which would be 1 watt. And you say, I absolutely need at least minus 50 dBm in order for this thing to work properly. Then somewhere between here and there, these terms have to add up to, at most, minus 80. In other words, you can lose at most minus 80 dB. So what we're going to see, we'll touch on this again next time, just to finish off the concept. Path loss, we've already done that. We've got an expression for that, and the path loss exponent will come into here. Multipath fading margin, what you want to do there is you want to have enough margin so that your probability of an outage, like I was saying in the slow fading case, your probability that your signal is going to drop is sufficiently low. These usually won't be too important in our applications. They'll probably be 0 or 3 dB maybe. This guy, this is what you would do if you want to account for the possibilities of users indoors. That's about 10 dB. It might be what you would use to account for rain or anything else you'd want to deal with. Question over here.
Would GTA include any sort of application you would do before transmitting the signal?
That would usually be in the transmit power. Generally, the gains in these expressions are usually only antenna gains, not amplification gains. Any other questions? Okay, so that's all I want to talk about there. So let's get on with the quiz.